Hello everyone, welcome to this video lecture. Myself Dr. Nazeer Ansari, Assistant Professor, Department of Mathematics, Madannapalli Institute of Technology and Science. This series is regarding the foundation of complex analysis. We will start with a very basic idea what we call it's a complex number system, and then we will move forward to the determination of finding the roots of the given complex numbers. For example, if you start with the counting system, for example, the first number system that we call it's a natural number system. So first number system, if you see the set of natural number system that we used to denote it by n, it was the first number system that was used to count system, right? So the origination of a complex number system, if you start to find the root of this equation, suppose I have equation x squared plus 1 equals to 0, and if you start to finding the possible roots of this equation, so you will end up with solving like something like root over minus 1, correct? Now this number root over minus 1, it was not present in the real number system, so that's why we start it's a number called as the complex number system. So basically if you see that root over minus 1, it's a we will represent it by I, correct? It's an imaginary number system. This is the imaginary number, this is the first imaginary number, and we will use the notation I, correct? Now in order to represent a complex number, we need two coordinate axes. The first coordinate axis will represent the x-axis, and the second coordinate will be the for the imaginary y, that we will use it as an y-axis. For example, so we will use the two coordinate axes, this one, and this one is the real axis. We call it as a real axis, and this one will call as an imaginary axis. Okay. So any number, any complex number, say z equals to a complex number. So complex number will be x plus iy. So where x is the real part of the complex number and y is the imaginary part of the complex number. In the similar manner, x comma y as an ordered pair, where the first component will represent the real part and the second component is going to represent the imaginary part. So anytime we will use the notation z to represent the complex number, and c, the capital C, is used to represent the set of all complex number. So if we are talking about the number which is on completely on the real axis, which is not, it's a real number. So that number, real number, can be represented by x comma 0. So 0 means the number is already present in the real axis. And if we are talking about the purely imaginary number that is completely present on the y axis, then we will represent that number by 0 comma y. For example, if you look into this diagram, so we have taken z as a complex number where the ordered pair is x comma y, which is also as x plus iy, where I is the imaginary number. Now if you see that number, suppose one number is this one number, this number. Now if you see this number x plus iy, so here x is representing this domain, this is the x, and y is the corresponding value of y. So this x is also, the notation is real part of z is known as x, and we have used imz, that means the imaginary part of the complex number z. Some of the algebraic, we will talk about very few basic algebraic property of a complex number. Okay, what we mean by the addition of a complex numbers, what we mean by the equality of two complex number, like that way. For example, let us consider z1 and z2 and z3 are any three arbitrary complex numbers. So z1 is represented by x1 comma y1, where x1 is the real as well as y1 is the imaginary, z2 in the similar manner, z3. So if you see, when we say that a two complex number z1 is equals to z2, what is the meaning of this line is that we are saying that x1, the real part x1 and the real part of z2 x2, there has to be same. Second is both the imaginary part of them is also need to be same. In the similar manner, when we are dealing with the addition of a two complex numbers, say z1 plus z2, the addition has to be a component wise. So for example, suppose we have a x comma y, x1 comma y1, and plus x2 comma y2, like the way we used to do the ordered pair addition in a n-dimensional vector space, same way. So we are going to go for the addition as a component wise. The first element x1 will be added to this one, and the second element will be added to this one. For example, these represent the complex number z1, this represent the complex number z2. So the addition is done in a similar way. Similarly, the subtraction will go in that way. Now the product is having little bit tricky idea here. So if z1 and z2, imagine z1 is a complex number which is represented by x1 comma y1. Z2 is again a complex number which is represented by x2 comma y2. So if in order to see this one, you can also say that x1 plus I y1, correct, and z2 is x2 plus I y2. So if you product them, x1 plus I y1 and x2 plus I y2, it's you have to go with the product of simple from that one distributive properties. X1 will multiply with x2, x1 will multiply with I2, but with an additional property. Is the additional property is that we have to use the I square is equals to minus 1, because I is nothing but the root of the x square plus 1 equals to 0. So the additional property, the moment you will multiply I y1 with I y2, so it will become I square y1 y2, which is I square will become minus 1, so it will come to the real part of that one. And the fourth property is you see the inverse of every multiplicative inverse of a complex number, non-zero complex number z1. So 1 by z1 is equivalent to this one. Fifth property is called something we call as a modulus of a complex number. So if z1 is a complex number, so modulus is the distance of that complex number from the origin. So if you see any complex number, for example, like the way we have done here. So for any complex number, if you see, so this was the z is the complex number. So when you take this distance, so this is what we call as a mode of z. So if you calculate this one, this is automatically it's kind of forming a triangle. So mod z is will be equal to the by Pythagoras theorem, it will be equal to the right angle triangle. So it will be equal to the x square plus y square. Okay. So this is the modulo formula for a given complex number. It represents the distance of a complex number from its origin. Okay. Now the most important part of a complex that we are going to discuss is the polar representation of a complex number. So for understanding the polar representation of a complex number, we need to understand two things regarding a complex number. For example, if z is a complex number, what we call is an argument of a complex number, and second thing is what we call as a radius vector. So in the real number theta, a real number theta in radian, that z makes with the positive x-axis. If you see this one, so suppose this is the real line, this is the x-axis, this is the y-axis, and this is the z1. Now this z, we are saying that the real number theta, this is the positive x-axis that we are going to deal. Any real number theta measured in radian, that z makes with the positive real axis. It's with the whatever the radian angle that z makes with the positive real axis is said to be the argument of z, and it will be, we will use the notation argument of z to denote the argument of z. So for example, if you see this is the complex number, so this one, if I start measuring from this one, so this is the angle theta. Similarly, if we also start measuring from there also, if you like go like that way, so this is also then argument, correct. Now if I go like that way also, and if I complete the circle, and again if I go like that way, like this way, this is also a argument of the complex number. In a short manner, we will saying that for a given complex number, what is an argument? An argument is nothing but the real number theta measured in a radian from the positive real axis. That's it. So we have to take the positive real axis as the point of measuring the angle of a complex number. So we know that any for a given complex number theta, it can have infinite possible values, including the negative as well as the positive, and as in negative as well as the positive, and the integral multiples of 2 pi. Why 2 pi? Because if you measure this complete angle of this one, so it is equals to 2 pi. So if you see the third point, those values that can be determined from the equation tan theta is equals to y by x, where the quadrant containing the points, these are the points which will help you to find the argument of a complex number. Now each value of a theta is called an argument of z. Any value, whenever you calculate the value, it will represent the argument of z, and the set of all values will be denoted by the argument of z. Argument of z will represent the set of all values that is denoted by the z. The principal argument of z. So there is another sub classification of argument of z, that is called the principal argument of those value of argument of z which lies between minus theta and less than equals to theta. So if you have an argument, so there is another subclass that is called principal argument, and the principal argument is nothing but it's also a one kind of argument of a set, provided there is a one extra condition that the principal argument need to satisfy. The condition is that value of the principal argument should lies between minus pi and it should be less than equals to pi. So if you see the last formula, this one we have the simple calculation. So any argument of z can be represented by the capital argument of z. This capital argument of z is called the principal argument, where we are writing the a capital that will be used to denote the capital principal argument, and if we are writing a in a smaller letter, that is called the normal argument, general argument. So every principal argument is also a argument, but every argument may not be a principal argument because the restriction of that one. So this simple formula that will help us to calculate an argument of a given complex number. So argument of z is equals to principal argument of z plus twice n pi, where n is any integer. Correct? So let me explain here. If you see it here, z is a complex number. Now, if I make a simple diagram, suppose this is my complex number z, right? And if you write this one, this is my line. This is the radius vector. Now, if we say this is, we know that this is the positive x-axis, correct? And this is the y-axis. So by the definition of an argument, it says that any theta which measured in a radian from the positive x-axis. Now, if you measure this one, suppose by the definition, this is one argument of z, correct? Now, if you measure like in the same manner, if you measure start from this one, and if you circle this completely, and then again you measure this one like that. This is also a kind of, this is also a one of argument. It's never saying that how you are going to measure, but it's only saying that the definition only tells you that to measure the radian from the positive real axis. That's it. So if you go, suppose if you go in a clockwise direction like that way, this is also a value of an argument. So by the definition, argument of z is a set which contain all the possible value of thetas. And then another condition was that one we discussed, that the principal argument of z. So the principal argument is also one kind of argument, but the only condition is it has to be greater than minus pi and it has to be less than equals to pi. This is the only two conditions. For example, if you see this one, so whenever if you look at this one, if you are going in this direction, that is called clockwise direction. If you're going in this direction, if you're moving in that direction, that is called anti-clockwise direction, correct? So if you go in this one complete circle, that is equals to 2 pi. Similarly, if you go in anti-clockwise, then again if you complete one, it is also twice pi. So if you're going in a clockwise direction, we will represent it by negative. If you go in the counter clockwise direction, we will use it as a positive number. So here if you see, if you go like this way, for example, if you go from here to here, say this one, so if you go like this way, counterclockwise direction, so this is from here to here, the total radian value will be how much? It will be equivalent to pi, correct? And if you are going from here to here, that is clockwise direction, so the total radian will be equivalent to minus pi. So what we are saying, that the principle that if you see this one, every time if any point is lying here, we will always cover that argument by that one. We can always cover. So we don't need to repeat again, like the way we have repeat here, right? We have come across the 2 times. So here we don't need to repeat. So for this reason, we can say that the principal argument of a given complex number will be a unique number. But the argument for the same complex number, there can have infinite choice for an argument, normal general argument, but for the same complex number, the principal argument will be always unique. This is the only difference between a general argument and the principal argument. Or one more thing is that if you have a complex number, there is a infinite choice to represent that complex number in a polar representation because of this argument principle only. Now, for example, if you see the first example, say -1 minus I. This is one of the complex number where real part is -1 and the imaginary part is also -1. Now, if you see this one complex number, if you go draw the graph, if you see this one, basically this complex number is the real part is also -1 and the imaginary part is also -1. Basically, it is lying in the say third quadrant, right? So this, suppose this is the number, correct? This is the number. Now if you see this one, suppose this I am drawing the radius vector, this is the radius vector, suppose this is equivalent to -1, and suppose this is also value is -1, correct? Correct. Now if you measure this angle, if you apply the perpendicular by base 1, then it will become something like tan theta will become like y by x, which is equals to -1 by -1, which will be equals to 1 by 1. So this is it, so theta will be equals to pi, correct? Theta will be equals to pi. But this is the main angle, this one. But the definition of argument, principal argument, is that we have to measure from this one. Now if you measure from this one, so this is pi. If you measure like this way, this total angle is pi, again you have to add here, so this is pi by 4, sorry. So this total angle is pi, and again you have to make this one, correct? Now if you see this one, if I add pi to pi by 4, correct, so it will be equivalent to 5 pi by 4. It's no doubt it is an argument, it's definitely an argument of that complex number, but is it a principal argument? We need to verify that one. Is it a principal argument? Now if you clearly see, this 5 pi by 4 is definitely greater than pi. So definitely it's not going to be a principal argument, but this is one of the argument, because if you see, we have measured from here there to this one, it was a pi, and since this angle is pi by 4, so if you add this one, the total angle is 5 pi by 4. This is one of the argument. Now in order to find the principal argument also, now if you see the same angle, if you go from measuring in the clockwise direction from the real positive axis, so this angle, total this angle, we need to find up to that much only. So that is one of the argument of this complex number. Now if you if you want to calculate this one, so we are going in the negative sense. So if this is total is a minus pi, if you subtract this one, so this will become pi minus, sorry, pi pi by 4 minus pi, so it will become minus 3 pi by 4, correct? From this angle we need to minus this one, so this will become minus 3 pi by 4. So this is one of the, this is, sorry, not one of the, this is the principal argument of the complex number. 5 pi by 4 will not be a principal argument of the complex number. So once you are comfortable with every complex number, how to calculate the principal argument and any argument of a complex number, so next will be our radius vector. What is the radius vector? Radius vector is nothing but if any number which is lying this one, suppose any position, suppose anywhere. So if you the if you draw the radius vector, so this distance, that is nothing but the modulus of z that we have discussed earlier, that will be the radius vector. So given any complex number, let r and theta be the polar coordinate of x and y. So by the normal theory of polar and Cartesian one, we can always represent x by r cos theta and y equals to r sin theta. So in that way, any complex number, if you see, any complex number can be represented by in the form of z equals to r under bracket cos theta plus I sin theta. So cos theta plus I sin theta is also equals to e to the power I theta by de Moivre's formula. So that z is equivalent to r e to the power I theta, correct? So this is the polar representation of a complex number. So now we have understand three ways to represent a complex number. The first one is any complex number z is equals to in the form of x plus iy, where I was the imaginary number, which is equivalent to root over -1. The only property is I square equals to -1. This was the first presentation. When you go to the second presentation, we said that we will represent the complex number in the Cartesian form, and we draw the Cartesian. One was the real axis, one was the imaginary axis. So the any complex number z was be represented by order pair x comma y, where x was representing the real number, sorry, real part, and y was representing the complex part. Now the third form that we got is a polar representation of a complex number. So given any complex number, I can always represent this complex number z is equals to r e to the power I theta, where theta is nothing but the argument of z. And what is r? R is the radius vector of a complex number. Now if you see the difference between these three presentation, so given any complex number, there is only one way to represent that complex number in the Cartesian form, that is either x plus iy or sorry x comma y. Now when we represented that complex number in the radius form, sorry, polar form, if you see, we have already understand that given any complex number, there are infinite choices for the radius vector, sorry, not radius vector, infinite choices for the argument of a same complex number. Now this theta in this polar representation is representing the argument. So by this manner, for any given complex number, I can have infinite choices for the polar representation. So we need to understand when we say the two complex number is equal and when we say that the two complex number is not equal. Correct. In the last line we have written said z1 is equals to r1 e to the power I theta 1 and z2 equals to r2 e to the power I theta 2. They are the two complex number. We will say that these two complex number are equal if r1 is equals to r2 and theta 1 is equals to theta 2 plus 2 and pi. Now this theta 1, we are not writing theta 1 is equals to theta 2. We are writing theta 1 is equals to theta 2 plus 2 and pi, where n represent any integers. For example, if you see this one, if you see this diagram, correct. Now any complex number z, suppose this was my complex number z, and this is my radius vector, this is my radius vector, and this is my argument of z, correct. Now if you draw this one, suppose this is the circle. Now if you start moving in this direction, correct, if you start moving in this direction, suppose we are moving in this direction and z is moving like a clock, suppose it's coming in this position, anti-clock position, suppose it's keep moving like that way, correct. Now after some time, if you see, when we rotate completely up to twice pi, again we are reaching to the same position, correct. If you measure with the twice pi, again we are reaching to the same position, correct. For example, if this is my number, now if you see the same z equals to r e to the power I theta was my number. So if I add this theta, if I increase this theta by twice pi, correct, if I increase this theta by twice pi, that means the theta was there, this value was the theta. So if I keep moving in this direction, correct, since we have already discussed that when we measure in the anti-clockwise, we will take as a positive one. So if you move in this direction, so this is theta plus, so if this total angle will become twice pi, so it will become theta plus twice pi. So if you see this complex number, they are already same. There is no distinct between them. Only thing is we have rotated the our one times the complete for this representation. So these two complex number are also same. But if you say when we represent z equals to say x plus iy, z1 was x1 plus iy1 in the form of z2 is equals to x2 plus iy2. So when we are saying that the z1 is equals to z2, what is the condition we need to verify? That x1 has to be equals to x2 and y1 has to be equals to y2. These are the two important conditions, and they are all necessary and as well as sufficient condition to verify that the two complex number was same, and that is in the Cartesian form. But the moment we enter into the polar form, z1 equals to r1 e to the power I theta 1, z2 equals to r2 e to the power I theta 2, we are saying that these two complex number are same if r1 is equals to r2 and theta 1 is equals to theta 2 plus 2 n pi. Why? Where n is nothing but n belongs to z. Similarly, why n can be negative also. So if we move in this direction, if we start by this direction also, the same way we will reach after 2 pi, we will reach to the same point. So the theta 1 should be equals to theta 2 plus twice n pi. So in short, the final conclusion will be two complex numbers z1 and z2 are said to be equal if they have the same radius vector, and the second one is their one of the argument is equals to the second argument plus twice n pi, where n is an integer. Okay. Now this observation, the observation that representation is an infinite choices, will help us to find the nth root of any given complex number. For example, if you are able to write z equals to r e to the power I theta, correct. Now if you say this one, z is nothing but r, also we know that it is equals to cos theta plus I sin theta, correct. Now if you see, if I write z to the power n for any n is a suppose integer, right, so it will become something called r cos theta. If you see, go by simple calculation also, it will become something called to the power n to the power n, correct. So this r to the power n is okay, no problem, because it's a real number. Now by De Moivre's theorem, if we know that, if you already know about the De Moivre's theorem, so it is equals to the cos theta plus I sin theta to the power n, then this n is shift to here. This is with the help of De Moivre's theorem, this n will shift to this one, correct. So this is nothing but by solving this one, z to the power n become e to the power I n theta. correct? So for any complex numbers, that nth power will become very simple, that is r to the power n e to the power I n theta. So this observation and the observation regarding the argument and third observation regarding the representation of a complex number in finite ways. So these three observations are going to help us a lot to find the nth root of any complex number. Okay, so first we will explain the method, and then we will see one example how to find the nth root of a complex number. For example, consider a complex number z naught equals to r naught e to the power I theta naught. This is the first any one complex number we have chosen, where n is has the value 2 3. Now this method start with the fact that the nth root of z naught. What is the nth root of z naught? The nth root of z naught is a number z, which can be r e to the power I theta, such that z to the power n equals to z naught. We are trying to find the solution of this equation. Z to the power n is equals to z naught. This is our equation, and we need to find all those z whose nth power is equals to z naught. Now, if you need, suppose let consider this z is equals to r e to the power I theta. Suppose in general arbitrary, suppose z this need to satisfy this z naught, and since this z naught is a complex number, it has to some form, say it is r naught e to the power I theta naught. Now we are saying that r e to the power I theta to the power n is equals to r naught e to the power I theta naught. Correct? If you want to solve this equation, z to the power n r e to the power I theta to the power n should be equals to r naught e to the power I theta naught. Correct? Now if you go to this one, so if you see this one, my z naught was r naught e to the power I theta naught, and we are trying to find all those z such that z to the power n should be equals to z naught. So let us take z equals to, let us take z equals to r e to the power I theta. In general, this is my arbitrary. Suppose this one will satisfy this equation number 1. So by simple calculation, r e to the power I theta to the power n will should be equals to r naught e to the power I theta naught to the power, sorry, not to the power, this one. So if you solve this calculation the way we have solved earlier also, this will be nothing but r to the power n e to the power I n theta, and this is equals to r naught e to the power I theta naught. Now this is one complex number, this is one complex number, and we have already seen that these two complex numbers, the statement is these two complex numbers are equal. What does this mean? This means that we need to have r to the power n should be equals to r naught, and n theta, this is the argument of this one, n theta should be equals to theta naught plus 2 k pi. So here I am using k because n is already there, so I am using k. The condition is only that n k belongs to z. Correct? So this implies what will be r? This r and r naught. If you observe this one, r and r naught are the real numbers. So r will become, something called 1 r to the power r naught to the power 1 by n, and theta, if you solve this equation, it will become theta naught plus 2 k pi by n, where k belongs to z. Correct? So this implies our z will be nothing but equals to r naught to the power 1 by n theta naught, sorry, e to the power I of theta naught plus 2 k pi upon n, where k belongs to z. So finally our z is equals to r naught and power root of r naught e to the power I of theta naught plus 2 k pi upon n, where n is fixed. Correct? N is fixed, and only thing is k is returning from, k is equals to 0 plus minus 1 plus minus 2, something like that. Correct? Which is equals to, which is nothing but integer. So for any given integer z naught, we have found that this z equals to nth root of z naught, nth root of r e to the power I theta naught plus 2 k pi by n is the nth root of z naught. Now this is the final way to represent the nth root of complex number z naught. So in this way we can always represent these are all the roots. Now if you see, we are able to see immediately from this exponential form that they are all, if you observe this one, this is nothing but, if you keep on changing that one, they're already, all of them are lying in a unit circle. that is a circle of radius 1, and all of them will lies in this unit circle in this one. So something like that, some position like that way, with the radius will be equals to this one, correct? Starting with an argument, this is the first argument. Evidently all of the distinct roots of 10 are further, and this final position will be, we will express this one to represent the complex root of a given complex number z0. So if you see that there will be, for a, suppose we are finding the nth root of z0, so there will be nth distinct roots, and that n distinct root will be given to us by substituting the value of k equals to 0, 1, 2 up to n minus 1. So for example, we are trying to find the nth root of 1. For example, let us take now z0 is equals to 1. Now we already know that 1 is lying here, correct? 1 is the position here. So its argument, what is the argument of this one? So argument is nothing but the radian measured in the, it's a theta, real number theta measured from the positive x-axis. So it's already in the positive x-axis, so we can take that one argument as equals to 0. So this complex number z equals to 1, z0 equals to 1, its polar presentation will be something of this form, 1 plus 1 e to the power I of 0, this one. Now this 1 to the power I 1 minus 1 by n will be equals to this presentation. By simple calculation we got that the nth root of unity will be represented by this one, and they will all lies in a unit circle whose of radius 1, and these are the k will be running from 0 to n minus 1. So sometimes many textbook will use this notation omega n to represent the nth root of unity, e to the power I theta, and this one w k to the power n will be represented in this way. Said omega n represent the nth root of unity, and sometimes we will use this. Many textbooks used to write in this way. Okay. Thank you.